welcome to the class again. We were discussing Woodward-Fisher rules for enones. Now we will see Woodward-Fisher rules for aromatic systems. Yeah, as far as aromatic system is concerned, we have 6 pi orbitals which are listed like this. As we know, there are 2 HOMO orbitals and 2 LUMO orbitals. Pi 2 and pi 3 are filled with electrons, and pi 4 and pi 5 are unfilled empty orbitals. Because pi 2 and pi 3 are having same energy, and pi 4 and pi 5 are having same energy, we do think that there is only one electronic transition possible in benzene. But in benzene, in fact, there are 3 electronic transitions possible. The more electron density on benzene disturbs its symmetry, so that instead of one electronic transition possible, now there are 3 electronic transitions in benzene. Okay, so these 3 are given here. Among these 3, 180 nanometers and 200 nanometers bands are called primary bands. 260 nanometer band is called as secondary band. Among the primary bands, 180 nanometers is allowed, 200 nanometers is forbidden. Similarly, 260 nanometers is forbidden. Sometimes it is possible to have these forbidden bands in the UV visible spectrum. So you can see a model UV visible spectrum. The peaks with highest intensity, these are called allowed transitions, whereas peaks with lowest intensity, these are called forbidden transitions. Forbidden transitions generally should not appear, but sometimes due to the relaxations in symmetry properties, they do appear in the spectrum. But because they are forbidden, their intensities will be very, very low. So allowed transitions will have highest intensity, forbidden transitions will have low intensity. Now when we look at the aromatic systems, of course we will have either electron releasing substituents or electron withdrawing substituents. All of them will influence the lambda maximum values of aromatic systems, but all of them will influence in a similar fashion. Okay, so there will be not much differences between the lambda maximum values when we have electron donating or electron withdrawing groups. Of course, to study there may be something. Okay, when you look at these things, electron donating and electron withdrawing, see these lambda maximum values are almost similar. Okay, of course they are different from pure benzene. Pure benzene lambda maximum is 203, but substituted benzenes, their lambda maximum values are increased. Okay, right. But for individually, we will look at the influence of substituents on aromatic carbonyls. This is for aromatic carbonyls using Woodward-Fisher rules. As you know, the next position to carbonyl substitution, it is called ortho, and the next position it is called meta, and the next one is para. So we will have ortho on both sides, meta on both sides, and fourth carbon is only one, so we will have one para. Now, the parent value when we have an alkyl group R, a ring residue, this R is part of alkyl group, a ring residue. That means if this carbonyl is a ketone, then the parent value is 246 nanometers. If the R is hydrogen, that means this carbonyl is part of an aldehyde. If the carbonyl is an aldehyde, then the parent value is 250 nanometers. If the carbonyl is part of carboxylic acid or ester, that means if R is OH or OR, ester, carboxylic acid or ester, then the parent value is 230 nanometers. So for aromatic, for carbonyls attached to benzene ring, if the carbonyl is ketone, the parent value is 246 nanometers. If the parent value is aldehyde, the parent, if the aldehyde, carbonyl is aldehyde, the parent value is 250 nanometers. If the carbonyl is carboxylic acid or ester, the parent value is 230 nanometers. Now, different substituents at ortho, meta and para will also influence the lambda maximum value. Now we will look at these influences. When we have an alkyl group or ring residue at ortho and meta, ortho it is we need to add 3 nanometers to the parent value. If alkyl substituent or ring residue is at a meta position, then we need to add 3 nanometers to the parent value, or if the alkyl substituent or ring residue is at para position, then we need to add 10 nanometers to the parent value. Similarly, for OH or O-methyl or OR groups, we will add 7, 7 and 25. For O minus, it is 11, 20, 78. For chlorine, it is 0, 0 and 10. For bromine, it is 2, 2 and 15. For amine, it is 13, 13 and 58. For amide, it is 20, 20 and 45. For N-methylamine, it is none at ortho and meta positions, but 73 at para position. For dimethylamine, it is 20, 20 and 85. And then we will sum all these additions. Okay, so please remember, please by heart this table. For ketone, parent value 246, for aldehyde 250, for ester or carboxylic acid it is 230. Alkyl or ring residues 3, 310, OR 7, 7, 25, O minus 11, 20, 78, Cl 0, 0, 10, bromine 2, 2, 15, amine 13, 13, 58, amide 20, 20, 45, N-methylamine none, none 73, NN dimethylamine 20, 20 and 85. We will calculate for some examples so that we will familiarize with these rules. Yeah, this is the carbonyl and it is part of a ring, so it is a ketone, and we have one ring residue at ortho position, one bromine at meta position. Since it is a ketone, the parent value is 246, ring residue at meta 3, so 246 plus 3 249, bromine at meta it is 2, 251, so altogether it is 251. So I did not give the detailed table, but still we can manage it, right? This is carboxylic acid, so the parent value is 230, and we have OH groups, 2 OH at meta, 1 OH at para. So 2 OH meta 7 plus 7, para 25, 14 plus 25, 39, 39 plus 230, 269. Similarly, we can calculate it for this. This is a ketone. So this table must be remembered to calculate the lambda maximum values of aromatic carbonyls. Now we will look at the effect of conjugation on lambda maximum. What is conjugation? Either it may be a C double bond C, alkene-alkene conjugation, or it may be a carbonyl and alkene conjugation. For example, when we look at the influence of conjugation on a carbonyl, look at this diagram. This ketone, this is the energy required for this pi to pi star transition. Of course, I missed the n to pi star transition. So we, for some time we will just leave the n to pi star transition. Now, when we increase the double bond conjugation, then what will happen? The energy required for pi to pi star transition will come down. How it will come down? When we have conjugation, you know, the energy difference between HOMO and LUMO will decrease. When we have conjugation, the energy difference between HOMO and LUMO orbitals will decrease. So with increase in conjugation, the energy required for electronic transition will come down. So that is what is called bathochromic shift or red shift. Either energy decreases or wavelength increases. Now, if you look at this argument in the case of ethene, 1,3 butadiene, 1,3,5 hexatriene. Now we can clearly see this. The lambda maximum in the case of ethene is 175 nanometers, whereas it is 217 for butadiene and it is 258 for hexatriene. And for beta carotene, it is 465. I'll show the structure of beta carotene in the next slide. So that means with increase in number of conjugation, the energy difference is decreasing for the electronic transition. Then, or in other words, we can say the lambda maximum is increasing. You know, conjugation not only have bathochromic shift, but it will also have hyperchromic shift. That means the epsilon value will also increase with conjugation. Please look at the epsilon values of ethene, butadiene, hexatriene, and beta carotene. The epsilon value is increasing. So increase in epsilon value is called hyperchromic effect. So the conjugation results in bathochromic shift as well as hyperchromic effect. Now we will look at the same argument in a different fashion. We will now consider the homo-LUMO of all these orbitals: ethylene, butadiene, hexatriene, and octatetraene. When we look at this, ethylene requires 165. Of course, there is a difference here. 175 it should be. Then for butadiene, it is 270 nanometers. For hexatriene, it is 256 nanometers. For octatetraene, it is 290 nanometers. So that means with increase in number of conjugation, what is happening? The homo-LUMO band gap is decreasing. So because of this decrease in homo-LUMO, the energy requirement for this electronic transition will obviously come down. So we observe bathochromic shift. Now, ethylene absorbs energy around 180 nanometers. With increase in one double bond conjugation, it is 217. With three double bonds, it is 256. With four double bonds, it is 290 nanometers. It is still in the UV range, right? What is visible range? Visible range is from 400 to 750 nanometers. Now, with increase in more and more number of double bonds, beta carotene observes a lambda maximum at 455 nanometers. Beta carotene, which looks like orange color, which presents in carrots, this is the reason for our vision. Beta carotene is the precursor of vitamin A. Vitamin A is responsible for our vision, right? So vitamin A absorbs the light in the visible region. So that is why we do observe objects in the visible region. So beyond visible, that means UV or IR, we don't visualize them. Why? Why? Because the vitamin A absorbs only visible radiation. So we can visualize the objects in visible range only. So the beta carotene absorbs at 455 nanometers and reflects the remaining light, so it appears orange color. So I will also discuss about the color of compounds. This is lycopene. With extended conjugation, it will have a lambda maximum of 470 nanometers. This example, para-nitroaniline. When you have conjugation, yes, of course, the electronic transition will be appeared at very low energy, right? But look at this example particularly. We have electron releasing group as well as electron withdrawing group on benzene. Of course, both of them will have their influences. Just sorry, I did not collect the lambda maximum value for this compound, but I'll still explain it. Here, the predicted value and the observed value, there is a huge difference between the predicted value and observed value. The observed value is even far less than the predicted value, what we calculate from the known rules. It is simply because of the synergistic effect between the two substituents. You know, amine group with its lone pair, it is an electron donating group. Nitro group is an electron withdrawing group. Of course, they will influence the electronic transitions. But see, in this example, nitro group and amine group both are para to each other, where in this case, the lone pair on amine can be directly given to the nitro group. So that means the electronic polarization will directly given to the nitro group. That means amine is donating and nitro group is attracting the electrons. So these two groups synergistically, they are influencing the electron polarizations. So because of that synergistic effect, the electronic polarization here is more even when compared to the normal molecules. So that is why for paranitro-aniline, the lambda maximum will be even less than the compared or predicted value. So the lambda maximum will be very, very less. Why? Because the two substituents are synergistically activating the electron polarization. So the polarization will be even more than the predicted. So that is why the lambda maximum value will be even lesser. Reverse, right? Energy will be lesser. So the lambda maximum will be higher. So energy, electronic transition energy for this molecule is lesser than the predicted. When we talk about lambda maximum, it will be higher than the predicted. Now, what is the color of compounds? As we know, with our naked eye, we can see colors, right? But what is the reason for color of compounds? Yeah, we do observe only visible light. So compounds which are interacting with visible light, they will appear to us so with different colors. White light, which is a combination of all the lights, that means VGR, when we mix VGR light, it appears white light. Okay, so when we pass a white light onto a material, onto a substance, then some of the light will be absorbed or will be absorbed by the molecule, and the remaining will be transmitted or reflected. Now, what is the lambda maximum which we are talking about? The lambda maximum which we are talking about is the energy of absorbed light. Energy of absorbed light. Then what we see, we don't see the light absorbed because it is not reaching us, right? The substance is absorbing the light. So the light is stopped at the substance itself. Then what we are seeing, what we are watching the light which is transmitted or reflected. So when the light falls on a material and it reflects, then we will see that reflected light. So that means whatever the lambda maximum we are talking about, it is the lambda maximum of absorbed light, and whatever we see is the color of the reflected or transmitted light. So that is what is called complementary colors. If a substance absorbs one particular light, then the remaining will be reflected. So that is what is called complementary light. For example, from this color wheel, you can clearly see if a substance absorbs red light, it emits green light. So that is what complementary means. If a substance absorbs red light, it emits green light. If a substance absorbs yellow light, it emits either purple or a violet color. If a substance absorbs orange color, it emits blue color, and vice versa. So this is what we call complementary colors. Okay, so whatever we are visualizing the colors, they are not colors of absorbed light. They are the colors are due to the reflected light. Remember that. We talk about the lambda maximum. The lambda maximum resembles the light which is absorbed. For example, in the case of beta carotene, as I said, it absorbs at 455 nanometers, but it appears orange color, right? So 455 is not the color of orange color. See 580 to 620, around 600 nanometers. Then what is 455? It is the color of blue light, wavelength of blue light. That means beta carotene absorbs blue light and emits orange light. So that is why beta carotene appears orange in color. But when we talk about the lambda maximum, we do write only 455 nanometers because the lambda maximum is a lambda of absorbed light. Okay, so from this table also you can clearly see the complementary colors. Now we will look at the solvents. You know, solvents are most important when we collect UV visible spectrums. We must choose solvents in such a way it should not mingle with the compound spectrum. Generally, we will take 200 to 700 or 200 to 900 nanometers UV range. Okay, so but below 200 we don't observe. Okay, why? Why? Because there may be many transitions which may not give proper spectra in that region. Right. So when you want to use solvent, the solvent should not appear between 200 to 900 nanometers. So solvents are, if they observe light below 200 nanometers, they are good solvents. Generally, we use 95% ethanol and water as the most common solvents. And solvents which are having conjugation or double bonds, they do absorb light more than 200 nanometers. So generally we avoid such solvents. Okay, so that is why we always use water and 95% ethanol as the solvents. Acetonitrile, then cyclohexane, 95% ethanol, hexane, methanol, water. These are best suitable for collecting UV visible spectra, but nevertheless, these are all different solvents which we use for collecting UV visible data. Now, how do we collect UV visible data? All organic compounds will be dissolved in a suitable solvent. So we prepare a dilute solution, then we will pour the dilute solution in the cuvette, we will get the data. If it is concentrated solution, we don't get proper spectra. So what we will do, we will dilute it further and further until we get a proper, that means a clear spectra. So as far as organic substances, it is a simple task. Just make a dilute solution, then take the spectra. Sometimes some inorganic compounds or organic compounds may not dissolve in any of these solvents. Then what we will do? If they are not soluble, what we can do, we can coat them on a glass sheet. Then we will place that glass sheet in place of cuvette. So we don't use cuvette. For undissolved substances, or simply you can say inorganic substances, we will make a paste and we will coat it on a glass substance. Then we will dry it and we will take the UV. So for organic samples, we will dissolve it in a solution. For inorganic compounds, we will coat it on a glass slide and then we will take the spectrum. Now, how these solvents will influence the spectrum? Solvents sometimes influence the fine structure of spectrum. What is fine? See, if you can visualize these individual peaks, this is fine spectrum. If we cannot visualize it like shown in dotted line, then it is not a fine structure. Non-polar solvents do not form hydrogen bonds with the compound, so the spectrum may not be affected. So when we use non-polar solvents, they don't have any hydrogen bonding interactions. So compound will not interact with the solvent at all. So whatever the spectrum we collect, it is mostly 99% from the compound itself. So we can purely say, though we have used a solvent, we can say the spectrum is from compound. But when you have polar solvents, then it is a problem. Polar solvents form hydrogen bonds with the compound. If your compound is ionic in nature or its dipole moment is high, then the compound and solvent will have hydrogen bonding. Solvent influence the lambda maximum via stabilization of either ground or excited state. There are two possibilities. Okay, it may decrease the ground state energy or it may decrease the excited state energy. Polar solvents generally shifts pi to pi star transitions to longer wavelengths. That means they will generally stabilize the ground state. Stabilization means lowering of energy. When the HOMO orbital is decreasing its energy, then the band gap increases. So that is why we will have, oh sorry, it's in a reverse case, right? It's in a reverse case. Yeah, I'll explain it. Leave this point. We will go for the next point. Polar solvents form hydrogen bonds with the ground state of polar molecules, but not with the excited states. This is a general thing. Okay. So mostly polar solvent stabilizes ground state. As a result, the N2 pi star transitions will appear at longer wavelengths. Sorry, longer energies, higher energies, or in other words, shorter wavelengths. Because polar solvents with hydrogen bonding stabilizes the ground state, N2 pi star transitions generally observed at higher energies or shorter wavelengths. It is also possible that sometimes polar solvents may also stabilize excited state. In that case, LUMO energy will come down, so that N2 pi star transition now appears at a lower energy or longer wavelengths. So the influence of polar solvents will be pronounced in the case of N2 pi star transition. For pi to pi star transitions, it is a general thing. For all pi to pi star transitions with now polar solvents, we always observe lower energies or longer wavelengths. Okay, right. So if you use a non-polar solvent, the compound will show clear peaks. If you use polar solvent, it may not show clear peaks. So this is the spectrum of phenol. Okay. Even I have also given a table where different polar solvents, influence of different polar solvents on the N2 pi star transition of acetone. You can clearly see from this, non-polar solvents doesn't have any influence, whereas polar solvents will lower their energies.